right, moving on to example 8. So example 8 is the culmination of all the derivative problems we have done all at once. In this problem, we're going to talk about a real-life situation that is modeled by a real function that's kind of messy. But typically in real-life problems, the functions are not pretty, which is why we're allowed to use our calculators. So in this problem, we're going to be modeling the spread of the flu, and P of T is the number of people infected, and T is the days after the flu was noticed. So T represents the days starting when the flu was noticed. So in this problem, I want to do 3 things. The first thing is I want to estimate the initial number of students infected. The second thing is I want to notice how fast the flu is spreading after 3 days. And the third thing is when will the flu be spreading at its maximum rate? And what is the rate? So I'm going to walk through these questions one by one really quick, and then we'll work them out. So again, here is our wonderful, beautiful function. And I rewrote it with a negative exponent because usually that will make our lives a little easier, because personally I don't like using the quotient rule, and there isn't a function in the numerator, so we only need the power rule. Part A says estimate the initial number of students infected. Well, this is commonly known as our y-intercept. And this is when t is equal to 0. How fast is the flu spreading? So when you see the words how fast, this is a rate. And so in our brains, we need to think derivative. And when will the flu be spreading at its maximum rate? So this right here, we're trying to find the max of the derivative. And then we're going to actually be evaluating it. Alright, so let's get started. Part A, we want the initial rate. So this is when t is equal to 0. So we get P of 0 is equal to 100 divided by 1 plus e cubed, plugging in 0 for t. And that's calculator work. Just type that into a calculator. And I'm going to put my answer as, here's my graph. As you can notice, I already went ahead and graphed it. So right here at this point A, we have the value of 4.74. Now remember, what does P of T represent? P of T represents people. So can you have 4.74 people? No. So our answer then is going to be 5. And I'm going to put a little explanation next to this. We need to round to the nearest whole person. Since P of T is in the units of people, so we need to start using our common sense and thinking, what can the answer actually look like? Alright, part B, this is very exciting. This is where this gets really fun. We want to know how fast. And so how fast translates to rate of change. And when we think rate of change, our brain should all go to derivative. So what that means, we got to take a derivative. So P of T is equal to 100 times 1 plus e to the 3 minus t to the negative 1. So then from here, we're going to take the derivative. So p prime of t. This exponent is going to come down to the front, and then we're going to minus 1. So we get negative 100, 1 plus e to the 3 minus t to the negative 2, and then we need to multiply by 1 plus e to the 3 minus t prime. We need to multiply by the derivative. Okay? So we get negative 100, 1 plus e to the 3 minus t to the negative 2, times the derivative of 1 is just 0, and then the derivative of e to the 3 minus t is, you just bring down the e to the 3 minus t, and then take the derivative of 3 minus t. Right? And this right here represents the derivative of just that little piece. So we get negative 100, 1 plus e to the 3 minus t to the power of negative 2, times a negative e to the 3 minus t, because the derivative of negative t is negative 1. And now we're just going to go ahead and clean this up a little bit. A negative and a negative make a positive. So you get positive 100 e to the 3 minus t divided by 1 plus e to the 3 minus t squared. And this represents dp dt, the derivative of people as in respect to time. So this is the change rate of the amount of people sick divided by the rate of time. So it's the amount of people sick in respect to time. Okay, and the question asked us, the whole point was how fast will it be spreading after 3 days? So we go ahead and we just plug 3 in to the derivative. 100 to the e 3 minus 3 divided by 1 plus e to the 3 minus 3 squared, which gives you 100 e to the 0 divided by 1 plus e to the 0 squared. So you get 100. Remember, anything to the 0 power is 1 divided by 1 plus 1 squared, which gives you 100 divided by 2 squared, which will give you 25. And it's very important to note our units. So in a question like this, you need to give a sentence answer. So the flu is spreading to 25 people per day after 3 days. Okay. And now for part C, this one we want the maximum rate. So I want to know, when is this thing moving the fastest? So just like before, when we want to find a maximum height, we would set the derivative equal to 0. We want to find the maximum of the rate. So we want to set the second derivative equal to 0. Okay, again, we do this because we want to know the velocity, when the velocity is a maximum. All right, so let's go ahead. Let's take the second derivative. So the second derivative of p with respect to time is going to be the derivative of the derivative. right? The second derivative is the derivative of the derivative. Okay? Now this looks complicated. This is not something that I want to take the derivative of. So the question is there another way? There's got to be another way. And fear not, for the answer to this is yes. All we have to simply do now is go ahead and look at the graph of the derivative. So what you need to do is graph the derivative. And we learned in an earlier section that we can actually graph all of this. Okay? So take a minute now in your calculator and graph. Okay, so I'm actually just going to show you how to put that into your calculator in case you don't know. So again, we're going to graph the derivative. Now you can either just graph the normal function and tell the calculator to graph the derivative, or you can just type in the derivative that we got. So I'm going to go ahead and type in the derivative here. So here is our function I want to graph, and here we go. So I have a fraction, so it's y equals, you get 100. To get to e, you push second, and then ln, and then 3 minus, and again here I'm going to push x. In the calculator, we're going to replace all of our variables with x. Open the parentheses, 1 minus e to the 3 minus x, drop down, close the parenthesis, and square it. And then go ahead and just push graph. Now your window might look different than mine. Oh, there's a slight typo in my work. Everything was right, except right here I copied down a minus where it should be a plus. So if you want to go back in the calculator and fix it, you go to y equals, and then you drop down here to the minus, and you put a plus. And your window might not look like mine, so if your window's a little different, just push zoom. I like to go with zoom 0, and the calculator will try to guess what the best window should be. And so that looks pretty good. And so to find the maximum, we're going to push second trace for calc, and then you can go ahead and find the maximum by going down to 4. And it's going to ask you for the left bound. So I'm going to left bound it over here. And I'm going to right bound it over here. That means that my maximum is going to be between these 2 points. And then the calculator asks you to make a guess. Well, it's somewhere up here at the top. Push enter. It'll think. And look at that. Maximum is 3 points, a bunch of zeros, and then a 3, 1. So we know the calculator sometimes has a little bit of error. So the maximum is x equals 3. I'm going to pull that up on a little bit of a nicer graph so you guys can really see what's going on here. Right here, I graphed p of t and then the derivative. Well, you can see right here, it's pretty clear that the maximum is 3 of this. And this red line represents the derivative of our original function. And that's it.